Okay. Sapling is up and live right now. I went through and picked some textbook problems. I will get Connect set up later today. Okay, so you'll have those problems. Just in the process of scanning through the textbook, I thought it was actually kind of interesting. There aren't a whole lot of problem types. Okay, so you're going to end up looking at the same types of problems again and again and again and probably again. Okay? So most of this is conceptually based, which means you have to understand where things are coming from. The first time I gave a thermodynamics lecture, it was awful. Okay? This is hopefully a little bit better, but we'll see. Okay? It was so bad that I gave up about half an hour through it, and it was an hour and 15 lecture. Sat on the front desk and just complained about how crappy thermodynamics was. Okay? And that's because I just couldn't get my head wrapped around the idea of what thermodynamics meant. The sequence within the textbook made no sense to me. I looked at 4 other lecturers' slides on what they did with thermodynamics. None of that made any sense to me either. Okay? So what we're looking at here, or what we're going to look at as far as the thermodynamics chapter goes, is a pretty drastically different spin than what you're going to see in the textbook. Okay? It's still going to cover the bases. It's going to come back to what you end up having to solve, but try and give you a little bit of an idea on why we look at it, where it's coming from, why did someone even think to come up with any of this information. Okay? And almost all of that comes back to energy diagrams, which again, we're going to tie back to at the end of this. Okay? So, ultimately, thermodynamics, it's the study of energy transitions. Okay? Thermo, heat, dynamics, motion. So we're looking at how energy is transferred ultimately between different environments. Okay? So to kind of get a feel for this, we want to know kind of when the chemistry works, but then how does it work? Okay? Is it something that will happen? Is it something that won't happen? We want to get kind of a better grasp behind what's happening with those energy transfers. Okay? So what I like to do is sometimes go back to physics, because at least with most things within physics, when it comes to mechanics, we can actually understand that and we can see that a little bit easier. So we're going to keep seeing these 3 figures show up. Okay? So if we take a look at these 3, which of the following, trying to get the ball from A to B, which is going to be the most likely? Okay, why would 3 be the most likely to get the ball from A to B? All we got to do is tap it, and what happens? It's at B. If we look at situation 1, it's not just a simple tap. We actually have to push that ball physically uphill. Situation 2 gets a little bit easier. We have to just push it, but on a flat incline. Situation 3, a quick tap, and we're already there. Okay? The energy of that hill is going to transfer over, and we can be nice and happy with that. Okay? And it comes back to kind of that negative slope idea. So if it works with physics, in theory, we should be able to make it work for molecules in chemistry. So if we went through and looked at this, what we can now start to equate is that 1, our ball is going to equal our chemicals. Okay? And we're not saying reactants or product at this point. We're just saying our soup of chemicals. Okay? As we move from position A to position B is when we're changing those chemicals from being reactants to changing them to being products. Okay? So what we're looking at is already an energy diagram where we're looking at the reaction progressing forwards. So we could call it the reaction coordinate. Okay? The relative heights of our A and B would be an energy inherent to those positions. So when we look at physics, in situation 1, the energy of position A is relatively low in comparison to the inherent energy at position B, which means we have to add a bunch of energy into it to get it up to that position, get it towards our products. Okay? And then the last thing is we can look at the force provided to the ball. Okay? How much energy do we actually have to supply to get it to move from position A to B? Okay? So it's a crude analysis, but it works fairly well. So we can start to go through and make some comparisons. Okay? The first one we'll evaluate would be step 2. Okay, why not step 1? Does anybody have any questions about step 1? Let's try it that way. No, it sounds fairly straightforward. We're either at reactants or we're at products. Okay, so we won't evaluate step 1 much more than that. Step 2 is a little bit difficult. We need an energy inherent to those relative positions. So we have to come up with some way to describe the energy at each of those positions. Okay? When it's physics, we can look at gravity and height generating a potential energy. Okay? Or we could even move to electricity and magnetism. I have no idea what their energy units are there. I didn't do so well in that class. Okay? When it comes to chemistry, we want to come up with some way to evaluate that energy. Okay? So in physics, we already said this, it's that change in distance, particularly when it comes to gravity, generating some force. So maybe it's just as simple for chemistry. So if we take a look at these 3 molecules, what is the inherent energy in each of these 3? How much energy does H2 have? How about methane? Helium? No volunteers. So now you're going to try and rank them. So why would you put methane highest?
Because it has 4 hydrogen molecules, 4 hydrogen atoms, and then 1 carbon atom.
So we could start to look at the numbers of atoms within each of these. But that still doesn't give you a number. Okay? That doesn't tell you an energy associated with it. That allows us to rank them. So ranking could work, but it still doesn't give us an exact number. What do you think? So we could try and look at bond energy. Okay, so when we first go through and do this, just looking at the atoms themselves or the molecules isn't the easiest. So what we can try and do is look for the bonds, which is where both of you guys went. Okay? One was looking at the number of bonds. The other one was looking at the energy within the bonds. Okay, so let's answer that question. What's the energy of that hydrogen-hydrogen bond? Still hearing some silence on that. How about the carbon-hydrogen? Maybe that's an easier bond. Or the helium? Helium doesn't have any bonds, so does it have 0 energy associated with it? Helium does have some energy associated with it, but it's not found in the bonds. So this is where our theory starts to crumble a little bit. Okay? And in particular, we have an issue. We can't monitor the direct energy between those. Why not? Do we know the energy of our hydrogen atoms separate, or our hydrogen atoms? Okay, we can't really figure out an exact energy. So now we've got a bit of an issue. Okay? But what we can go through and do is look at another situation. Let's take a look at methane. I like methane just because it's organic, sort of. Okay? What's the difference in energy between a carbon-hydrogen bond that was made when we used carbon solid versus carbon gas? Okay, I know I changed the phases on the hydrogen, but let's say we even stick with the same hydrogen gas. Okay, if I use carbon solid versus carbon gas, is the energy of the carbon-hydrogen bond change? It's still a bond between carbon and hydrogen. Okay? So that energy doesn't specifically change. So it doesn't matter necessarily how we make that bond, as long as we've got it. Okay? So this brings up an interesting idea behind this. The internal energy of our system is going to be known as what's called a state function. We don't care how we get there as long as we're there. Okay? So we can look at our differences in energy, but we don't care how many steps we had to go through to get to that individual state. Okay? Which seems like a relatively simple idea, but it gives us some important stuff. Okay? That important stuff is then how do we measure that internal energy? What we can do is instead of looking at an exact energy for an individual bond, we can look at the difference in energy from where we started and where we ended. Okay? And we can take into account all of the individual steps, add everything up, and we'd be able to get an enthalpy, an energy for that bond, okay? Or a change in energy in the formation of that bond. Not a direct measurement of the bond energy itself, but a change. Okay? And we would assume that that is relatively close to the actual energy of the bond. Okay? Yes, we're going to be missing some things, and it probably goes back to quantum physics and mechanics and all that fun stuff. But that's a relatively small contribution to the energy, and we won't worry about it. Okay? So what we can go through and do is change this energy in the bond to a different application. You've already seen the energy in the bond before. What is it? What do we call the energy found within any individual bond? It's the enthalpy. Okay? And we use the symbol H because H is just an obvious symbol for enthalpy. Because there's an H in enthalpy, right? There's a silent H at the front, right? Okay? So we can look at changes in enthalpy for an individual reaction or individual types of bonds, but we can't look at just the bond energy itself. Okay? So we can look at a final minus initial to give us that change in enthalpy in the course of making that bond, okay, from individual starting materials. Okay? You should go, oh, I should check that chapter reference. I will check that and let you guys know what it is in the, what do we use, Chang? The Chang? It's chapter 6. Okay, I'll double check that just to make sure. But you should go back and review the Thermodynamics chapter from 151. Okay? We have on reasonable authority that it's chapter 6. Okay? So there's certain things that you should remember from that chapter because we're not going to discuss it in great detail here. Okay? Our first law of thermodynamics, okay, the internal energy of an isolated system is constant. Okay? Said other ways, we can't create or destroy energy. Okay? One of the new, I think it's new, concepts that we'll bring in is this equation. Have you guys seen this equation already? Yeah? Okay, U is our potential energy. Q is heat, and W is work. Okay. Where this can come into or be a bit of a pain is, of course, when we come back to signs. Thermodynamics is going to be a pain when it comes to knowing what signs each of your values should be. Should it be positive or should it be negative? So if we're going to look at the potential energy, okay, of a system, in particular a change in potential energy, and our reaction does work on the environment, did it lose energy or did it gain energy? It lost it. We moved something else. Okay? Our system had to give off that energy to cause that something else to happen. What happens if the environment does work on our system or on our individual reaction? Now that increases the potential energy. So what we're looking at is a positive value for our work. How about with our heat term? What if we see a negative heat? What does that mean? It's exothermic, and our reaction lost energy. It lost it as a form of heat. Okay? So problems that you could see on the exam or your practice exam, and I'm not positive if I'm getting it confused with 151 or not, is being very, very careful with the signs on those terms. Okay? And those signs are ultimately going to be interpreted from English. Okay? So make sure that you apply those appropriately when you go through and determine that. That calculation itself is relatively simple. Okay? So if we said the heat was 2 without a sign attached to it and the work was 3, possible answers. What are possible answers that we could get on a multiple choice exam? What was that? Okay, so we could get positive 5 if we just added them all up. What if they were all negative? Negative 5. What if the heat was negative and our work was positive? We would get positive 1. What's the last answer? We could get negative. Let's try that again. Negative 1. Okay? So we get 4 possible combinations of adding and subtracting these things, which means Where your work, as far as this problem is going to come in, is trying to decide in that little space in front of these, what sign is it? Is it positive or is it negative? Okay? That translation is up to you. And we just talked about a few of those. If work was done on the system, what happened? Positive work. Okay, we added energy into it. Our potential energy must go up. Okay? If we lost heat, has to be a negative heat term because we lost that energy. What if it was exothermic? Exothermic is again negative. We would expect our heat term to be negative. Okay? So there's a variety of ways to refer to those positives and negatives with the use of the English language. Make sure you're using them appropriately. Okay? Next part, at constant pressure, one of the things that we learned was delta H was equal to Q. Why does that happen at constant pressure? If the pressure doesn't change, it's very difficult to get a change in volume, which is how we would get work. Okay? So our change in enthalpy will equal the heat transferred. We use this when we look at calorimetry, okay, back in 151. Another big thing is dealing with signs. Delta H less than 0 means it is all sorts of answers I'd accept on this. It would be exothermic, and it would also mean that our delta H was negative. Okay? If you don't like negatives and positives, sorry, this chapter is rife with it. Okay? If delta H was greater than 0, what does that mean the sign is? Positive, and it has to be an endothermic reaction. Okay? One of the last things that you should have seen was your Hess's law relationship. We will come back to a few different variations of the Hess's law. It might even show up on the next slide. I just ran out of space. Okay? What we can look at is the energy of formation of your products minus the energy of formation of your reactants gives you the overall enthalpy of that reaction. Okay? Which brings up an issue. How do you find out the enthalpy for your reactants and products? You're going to have to use the back of the book. A lot of the questions that you will for sure see in the textbook, because I just read through those today, and probably in Sapling, are again going to assume that you look up these numbers. Okay? So if you don't see it immediately given to you, you should assume that those numbers are things that you're supposed to be referencing. Okay? Which gets a little bit dicey because depending on the table of thermodynamics, you might get slightly different numbers. In theory, the slightly different numbers, when you enter them into Sapling or Connect, would take into account the rounding errors that's ultimately happening with those, and you should still get the answer correct. Okay? The easiest way to minimize those rounding errors, or the issue between different numbers within different thermodynamic tables. What's that? Use one table, and there's one table in particular you should be using. The one in the textbook. Okay? Or if Sapling, I think Sapling does give you a list. You can use the one that Sapling gives you. Okay? As far as Connect, use the textbook. As far as Sapling goes, if they tell you, here's a list of values, use that list of values, because that's what they are using to determine their numbers. Okay? So I said we weren't going to talk about any of that, and I spent 5 minutes. Just like me. Okay? So how do we make sure that our reaction actually works? Okay? So according to our theory, we would look at a delta H being less than 0. So we could say our reaction works when our delta H is negative. So for which of these transitions do we get a delta H that's negative? 3. What did we say according to our physics, which was the easiest one to do? 3. Hey, that's kind of cool. Our theory seems to match with our physical values for our exothermic reactions. Okay? But, there's always a but. Delta H less than 0. So let's pick a couple reactions where our delta H is less than 0. If we take HCl and NaOH and add it, or mix those together, we generate water. I did a good job balancing, so I had to scribble that in, and sodium chloride. What type of reaction did we just do? It's an acid-base reaction. You'll notice it's not equilibrium. Why is it not an equilibrium reaction? Because it's a strong anything, acid and base in this case. Okay? What do we know about acid-base reactions, or hopefully what you know about them? Those of you in lab should know this from dissolving your sodium hydroxide. We generate water in a salt, which is already up there. What else do we know? It also generates heat, which means it's an exothermic reaction. We've got a delta H less than 0. Does this reaction occur? Yeah. We mix these together, we get that heat, it dissolves, or those things react, and we can measure the heat. We can also measure the loss of acid and the loss of our hydroxide in the course of that reaction. Okay, so far so good. Our delta H is for sure representing that this reaction does occur. Okay, how about the next one? We take water, liquid water, and we take it to a solid at 0 degrees Celsius. Okay, does that reaction occur? Yeah, that's also an exothermic reaction, so that seems to make sense, except there's a little bit of an odd thing here. Why did I include the temperature? My theory so far is just looking at enthalpy being less than 0. And when we look at enthalpy, there's nothing in it about temperature. So this little introduction of a temperature here seems a bit odd. Okay? Everything's still holding, everything's still working, but it's not quite taken into consideration our temperature. So what happens if we kind of push this a little bit further? Okay? What if our delta H is greater than 0? So now what we're going to assume is that reaction shouldn't occur. Okay? So let's go through and take a look at a reaction where the delta H is greater than 0. Let's take a look at solid going to a liquid. Okay? Solid going to a liquid at 1 degree Celsius. Does that reaction occur? What's the melting point of water? 0 degrees. If we're above 0 degrees, do we see the liquid going in, or sorry, a solid going into a liquid? Yes, that reaction absolutely does occur. Why is that a problem? Our delta H is positive. According to our theory so far, if our delta H is positive, that reaction should not occur. Okay? So something about our initial interpretation is wrong. We know the delta H is related to whether or not our reaction can occur, but it's not perfect. It doesn't take into consideration our temperature, and it also doesn't explain why solid going to liquid should occur. Okay? So we have to account for something else. Okay? So we have to go back and now change our theory. Okay, so let's go back to our parallels. Okay, we could look at those relative heights again. Okay, did we assume something that wasn't true? If we took each of those three situations, those physical situations, and we just placed the ball there, okay, we could expect 3 to actually occur, and maybe B or 2 would occur. And we would never expect 1 to occur. Okay? But what happens if the ball was already moving? In our initial statement, what we're saying is that ball is not moving. Okay? It doesn't have any energy associated with it until we put it into it. Okay? That's a pretty big assumption. It works in physics, but it doesn't work in chemistry. So let's go through it, and it's, okay, now I got to start this. This is my first attempt at animation, by the way, and it's now 6 or 7 years old. Okay, let's say our ball was actually moving. See, it's rolling back and forth. See, yeah, it's kind of cool, right? Our ball is actually moving. Okay, it already has some energy associated with it. So now when we compare steps 1 to 2 to 3, which one looks like it's going to be the easiest? Well, in step 1, it's already at B. It's already made it to our products. Okay? So there's some other characteristic that we're not taking into consideration. Okay? So what does that mean? We're missing that kind of initial temperature and motion energy. As we increase the temperature, we increase the motion of the particles, and that's how we can start to transfer or transition in reactions where our enthalpy says otherwise. Okay? So now what we've got to go through and do is take a look at our motion and see what happens with it. Okay? And as we just evaluated already, okay, what happens to the motion when our temperature increases? Also increases. So we see a direct relationship between those. Okay? So what's happening? So our example that we used before where our theory failed. Okay? When we're moving from solid to liquid at 1 degree Celsius and our enthalpy was positive. Okay? What's happening to the motion in the example, in this problem? How are we increasing the motion? If I put a solid brick of ice on the table, is it going to move? Shouldn't move unless somebody hits it. But if I now increase the temperature to the point where it can transfer into a liquid, what happens to now our liquid water? Does it stay in that exact same shape? No, what happens? It moves. So in the process of transitioning from our solid to liquid, we are drastically increasing our motion. Okay? So the thing that we now need to incorporate into our theory is not just the energy of our bonds, okay, back to our enthalpy, but now also look at how motion can contribute to an energy term. Okay, which seems kind of odd, which is why we do it in second semester. Okay? Questions about that yet? Okay. So are we really looking at motion? So this is where it gets even more dicey. Okay? Can we come up with a better way to define it? Okay? So let's take a look at another example. We take a look at, so this is initial state. These are ultimately the same chamber. So we're going from, we're going from A to B. And in the process of going from A to B, all I do is remove that barrier. Okay. If we look at each of those individual particles, it won't change the temperature at all. Each of the individual atoms or red balls within A will move. Okay. What happens when we go to B? Do they stop moving? Do they really increase in moving? No. So it's not so much just a direct motion that's changing. Okay? What does increase? Okay, volume, and it's ultimately the number of positions, the possible positions those red atoms can be in. Okay, which, believe it or not, we can tie it back to motion. Okay? So what we're looking at is something a little bit odd. We have a little bit of a temperature drop here, which I don't want to get into. No bonds are altered, so our enthalpy change is 0. We don't really increase the motion, but what we do get is still a spontaneous reaction. It still actually occurs. Okay? So what ends up changing is the number of possible positions that each of those things can be at. So we're changing our number of locations. Okay? So it's kind of an interesting idea. We're not so much changing the amount of motion, but the amount of possible motions. When we look at state A, there was a 0 probability or a 0 possibility. Don't you love those funny sounds? A 0 possibility of being in that section of our chamber. As soon as we remove the chamber, we now increase that. Okay? There's now more possible locations for it to be. Okay? So it's kind of an odd idea. We don't really see it necessarily an increase in motions. We just see an increase in possible locations, if you will. Okay? So what can we do with all of this? Okay? When we look at motion, it's not just looking at how fast an individual particle moves. It's also looking at the space in where it moves. Okay, so our motion is defined by these three ideas. We can get a translation, okay, x, y, z, which we saw in that last example. We can move from position A, or one side of the chamber, to the other side of the chamber. Okay, it's a translational increase in motion. We can also look at a rotation. So an individual atom, if we look at solid to liquid, in the solid state, can an individual molecule spin? It's locked in place by all the other atoms. As soon as we move to a liquid, now it's no longer locked in space, and what happens? It can flip and rotate. And then the very last thing that we can look at as far as a motion is then vibration, an internal motion. Okay? When you get into organic chemistry, that internal vibration is something that we can actually detect with very specific pieces of spectroscopic instruments. Anybody happen to know what instrument you would use to figure that out? A spectroscopic one, very good. Missing two key letters in front. IR spectroscopy studies vibrational modes. Okay, what does IR stand for? Infrared light. We can shine infrared light on an individual molecule, and we can detect how its vibrational states change depending on the energy of light we hit at it. Kind of neat. Okay? So if we go through and look at each of these things, we can then evaluate back to these individual motions. Okay? Oh, well, that's close enough. Motion's kind of a boring name. Everybody knows motion. Since we're scientists, we like to make stuff up just because we want to sound cooler. So what we end up coming up with as far as describing this in a scientific fashion is instead of calling it motion, we can refer to it as entropy. Okay? Why did we pick entropy? Okay, if you trust Wikipedia on this. So first off, actually not quite first off. Why do we call it entropy? I believe, and again, it's Wikipedia as a source, but Wikipedia is half decent. Entropy was discovered much later after energy and enthalpy. Okay? And so the first two people that came up with energy and enthalpy were like, oh, these are cool terms. They're really important. You know, everybody should pay attention to energy and enthalpy. Okay? Well, then the guy that came along to discover entropy, nobody really liked him, apparently. I might be making that up. Okay? Decided that this entropy term was really, really, really important. Okay? And he wanted to make sure that people saw it as important as energy and enthalpy. What easier way to make sure that people actually start saying it than to pick a term to describe it that is very similar to the other two terms? So when you look at enthalpy, or try and say enthalpy versus entropy, how much of a difference is there? Not much of one at all. That was done intentionally, really nice guy, okay, so that people would, in theory, slowly pick up the idea that entropy is important and that it does need to show up in each of our calculations. Okay? Kind of obnoxious. But that's where it's coming from. As far as symbols go, okay, it's always nice to pick a symbol that makes sense. Enthalpy we had as H. Energy we typically use as E. So if we go to entropy, we need a new symbol to represent it. Okay? E's already been taken, so we have to come up with something else. The something else we come up with is S. And that's because this guy was from the Czech Republic. And it turns out that the Czech word for motion is stovat, or something along those lines. Okay? Feel free to look that up. It's completely not true. So what do we understand about these? That these two things are related to each other, and somehow they need to contribute to the idea of inherent energy. Okay? Yes?
Did you say look it up because it's completely not true?
I was waiting for that. Yeah. Stovat is completely made up. Okay. S is the right term, but I'm not even positive that stovat actually means motion in Czech. It might. I think it does. Okay? But now you won't forget. What's the symbol for entropy? S. Okay? So we can go back to looking at our individual motions. If we increase entropy, what we're really doing is increasing the possible number of different motions. So we're looking at increasing either our translational, rotational, or vibrational modes. Okay? So we want to come up with a way to define it. Okay? One of the more strict representations is that it represents our combined energies associated with all motions. So if we look at an entropy term, it's not just the translational motion, not just the rotational or the vibrational. It's a sum of all of the energies associated with each of those transitions. Okay? Which gets a bit difficult to calculate, so you don't have to worry about that because you won't have to calculate it. Okay? So what we want to do is come up with something that we can actually ask you. So what we want to do is look at how can we determine a magnitude or a change. Okay? And I do kind of want to get through this because then you can actually start doing homework problems. So we'll get to an idea on this. So what we're going to do is evaluate a couple different situations and decide, did the entropy go up or did it go down? Almost. Entropy, it is a state function. This is Hess's law, except it's now been changed around to represent entropy. Okay? So if you want to know the change in entropy for a reaction, you can look at the entropy of your products minus the entropy of your reactants. Okay? Make sure you take into consideration what I've got in there is N and M. Those N and M come from the coefficients in your balanced equation. Okay? I don't expect you to have these memorized, the molar entropies for each of these species. As far as the textbook goes, I expect you to look them up. Oh, man. You do have it in your appendices. I'm pretty sure it's not that page reference, though. So I'll get that fixed as well. When it comes to the exam, I will provide a table of possible values. Okay? Either a table or within each individual problem. I'll just list them off for you. Okay? So you will be expected to run those calculations. So we won't calculate. Oh, see, I knew I had a reason behind this. So as far as that calculate part, we won't have to worry too much about calculating. It's just that Hess's law problem, except now instead of enthalpy, we use entropy. So the next idea is to determine kind of a magnitude or change. This is where we're getting into the positives and negatives. I think I'm out of time. So what I'm going to do real quickly here. I know, it's real fast. We'll talk about it all the way through tomorrow. Where's my summary? There's a whole bunch of rules. These sequence of rules are things that you'll end up using to kind of apply looking at your changes in entropy. Okay? The only reason I'm skipping to that now is so that you can get an idea on how to work at least some of your homework problems. Okay? So at this point, you know how to calculate entropy and enthalpy by using Hess's law. So you look up tables, and now you have at least some rules to allow you to determine the magnitude differences. Okay? So is it positive or negative? We will start tomorrow with those rules.